Hello everyone, welcome to the paper discussion session for part test 17 chemistry. So let's proceed to the first question over here, question number 51. In the first question, we need to find out the stability of the hydrides, correct order for the stability of the hydrides, we need to determine that. Now all these are hydrides of group 15 elements, nitrogen, phosphorus, arsenic and antimony. Now down a group, because of increase in the size of the elements, what will happen? The bond length of the hydrides will also increase. So down a group, because of increase in the value of principal quantum number, size will increase. Now stability of any molecule is basically determined by the strength of the bonds present inside that molecule. The stability of any molecule will be directly proportional to the bond strength. Now stronger the bond, it basically signifies more amount of energy is required to break the bonds, so higher will be the bond dissociation energy. And we know bond dissociation energy is inversely proportional to bond length. So shorter the bond, it basically signifies more amount of energy is required to break the bond, matlab the bond is very much strong. And longer the bond, it basically signifies we have to supply very small amount of energy to break the bond, so that's why the bond strength is less and stability of the molecule will also be less. Now in ammonia, NH3, there is NH bond. In PH3, there is PH bond. In ASH3, ASH bond is present, and in SBH3, SBH bond is present. So ammonia belongs to principal quantum number 2, belongs to the second period, phosphorus belongs to third period, arsenic belongs to the fourth period, and antimony belongs to the fifth period. So down a group, because of increase in the value of principal quantum number, size will increase. So this is the scenario of overlap for nitrogen and hydrogen, both are having small size, so their bond length will also be less. Now down a group, when we are moving from nitrogen to phosphorus, obviously the size will increase, but the size of hydrogen will remain unchanged. So that's why the bond length will also increase, right? Again, when we are moving from phosphorus towards arsenic, then this will be the scenario of the ASH bond, right? Size of hydrogen is quite small, but the size of arsenic is quite large. So again, we are able to see increase in the bond length. Again, when we are moving from arsenic towards antimony, antimony is having the largest size of all the elements which are present over here, so this will be the bond length. So clearly we are able to see, because of increase in the size of the central atom over here, there will be increase in the bond length as well. So in SBH, the bond length is quite large, right? So if I supply very less amount of energy, then also I will be able to break this bond. So BD will be less. Obviously, if less amount of energy is required to break the bonds, bond strength will also be less. So if the bond strength is less, stability of the molecule will also be less. So that's why SBH3 is the least stable molecule and NH3 is the molecule which is having the highest stability. So that's why A should be the correct answer. So let's proceed to the next question. Question number 52. Okay. In question number 52, I have to actually check whether the properties which are stated against the options are correct or not. Okay. So let's check option A over here. So this is HF, HCl, HBr and HI. So again, on moving down the group from fluorine to iodine, what we are able to see, because of increase in the value of principal quantum number, size will also increase, right? Now on moving down the group, because of the increase in the size of the halogens, the bond length will also increase. So the concept is same as that of the last question. So HI is having the longest bond, since the value of bond length is quite high, so the value of bond dissociation energy will be quite less. Bond strength will also be very much less. So that's why if I supply less amount of energy, then also I will be able to break the bond. So after breaking the bond, it will dissociate into H plus and I minus. So H plus will be readily available, right? Since less amount of energy is required to break the bonds, so that's why H plus is readily available. So that's why HI is having the highest acidic strength. And obviously, since the HF bond is very much strong, obviously it cannot be easily dissociated into H plus and F minus, and that's why it is having the least acidity. So the order is correct for the property which is stated against it. Now let's check option B. In option B, group 15 hydrides are provided over here, right? These are all group 15 hydrides. Now we have to check their basic strength. Now all of these are actually Lewis bases. Now what are Lewis bases? Lewis bases they are basically lone pair donors. Lewis bases are basically lone pair donors, right? Now when we are moving down the group from nitrogen towards antimony, what we are able to see, because of increase in principal quantum number, size will also increase. Now in antimony, this lone pair electron cloud will get delocalized. Obviously larger amount of space is available in antimony. What is the principal quantum number of the outermost shell of antimony? That is actually 5. So obviously large amount of space is available for the delocalization of the lone pair electron cloud over here. So if the lone pair of electrons are getting delocalized, then the tendency of the central atom to donate the lone pair of electrons to any other substance will decrease. So obviously because of delocalization of the lone pair of electrons in a particular molecule, the tendency of the central atom to donate the electron cloud to any other substance will decrease. So basicity will decrease. In ammonia, less amount of space is available for the lone pair, so the lone pairs will not get delocalized. The lone pairs will rather remain concentrated on nitrogen only, right? So that's why in ammonia, nitrogen can easily donate the lone pair of electron cloud to any other substance. So that's why ammonia is the most basic over here, and down a group, because of increase in the tendency of delocalization, the basic character will decrease. So again the order is correct with respect to the property that is stated against it. Now let's check option D over here. CO2, SiO2, SNO2, PbO2. Now these are all group 15 elements, and what are the oxidation states? The oxidation states of all these elements is actually 4. Now we know because of inert paired effect, Pb plus 2 is more stable than Pb plus 4. That is because of inert paired effect. Because of inert pair effect, we also know stability of higher oxidation state actually decreases down the group, and stability of lower oxidation state actually increases down the group. So because of decrease in the stability of the higher oxidation state, that's why Pb2 plus is more stable than Pb plus 4. That is because of inert pair effect. So in PbO2, lead is present in plus 4 oxidation state. Obviously this is unstable, so lead is having high tendency to get converted to plus 2 oxidation state. So lead is having high tendency to undergo reduction, and as a result lead will try to oxidize the other substance. So if lead is having high tendency to undergo reduction, so I can also conclude lead is having very high tendency to oxidize the other substance. So PbO2 has the highest oxidizing power, and the oxidizing power will keep on decreasing when we are moving from lead towards carbon. So D, the order is correct against the property which is stated against it. So C is the only option in which the orders and the properties are not matching at all, So that's why C should be the correct answer over here. Let's proceed to the next question. In alkaline condition, KMnO4 is getting converted to K2MnO4. So what is the oxidation state of manganese potassium permanganate? That is plus 7. How we are doing this calculation? For potassium, what is the stable oxidation state? That is plus 1. Let us consider the oxidation state of manganese to be plus x. And what is the stable oxidation state for oxygen? That is minus 2. So minus 2 into 4. What is the overall charge on this molecule? That is 0. So what is the value of x I am getting? That is plus 7. So manganese is present in plus 7 oxidation state in KMnO4. As per this reaction, KMnO4 is getting converted to K2MnO4. Similarly, if I calculate the oxidation state of manganese in K2MnO4, I will get the value to be plus 6. So what is the N factor of KMnO4 in this reaction? The value of N factor is equals to 1. N factor is basically the change in oxidation state into number of moles of manganese which is present in 1 mole of manganese. So clearly we are able to see in 1 mole of KMnO4 only 1 mole of manganese is present. So N factor is equals to change into number of moles of manganese. So 1 into 1, the value of N factor for KMnO4 in this reaction is actually equals to 1. Right? Now we need to calculate the equivalent weight of KMnO4. Equivalent weight of KMnO4 is basically the molar mass of KMnO4 by N factor of KMnO4. Now how we can calculate the molar mass? For potassium the value is 39. For manganese the value is 55, and for oxygen the value is 16. So 16 into 4. So after adding all this value, you will get the value, you will get the molar mass of KMnO4 and you will get 158. So what is the value of equivalent weight? That is molar mass by n factor, molar mass by 1. So equivalent weight of KMnO4 in this reaction is also 158, and that's why A is the correct answer. So next question, question number 54. Let's check from option D. Oxalate ligand is present. Now this is the structure of oxalate, C double O minus, C double O minus. So this is a bidentate ligand with same donor site, oxygen is the donor site. So I can represent this complex in this manner. M is the metal and AA is the bidentate ligand having similar donor sites. So in MAA3, how many possible orientations are possible? How many possible orientations are there? So this is the only possible orientation, right? So clearly, because of the presence of the 3 chelate rings, the molecule will exhibit optical isomerism, but the molecule cannot exhibit geometrical isomerism. So only optical isomerism is being shown by this molecule, right? Now let's check option C. In option C, the complex is of the form MA4B2. So A and B both are monodentate ligands, different monodentate ligands, A and B. So A is ammonia I am considering in this example, and B is chlorine. Now MA4B2, how many possible orientations are there? So this is one possible orientation, one possible isomer. BB are cis to each other, and another possible isomer is this. So in this case, B and B, they are trans to each other. So here cis trans isomerism is possible, so it can exhibit geometrical isomerism, but due to the presence of horizontal plane of symmetry, optical isomerism will not be exhibited. Obviously, because of the presence of horizontal plane of symmetry, upper end of the molecule is actually the mirror image of the lower end. So that's why it cannot exhibit geometrical isomerism, right? Sorry, it cannot exhibit optical isomerism. Geometrical isomerism is possible, but optical isomerism is not possible. So this one is trans and this one is cis. So geometrical isomerism is possible, optical isomerism is not possible. Now let's check option B. So this is of the form MA5B. In MA5B, neither geometrical isomerism is possible, nor cis trans isomerism is possible, nor optical isomerism is possible, right? So this is the representation MAA, AA, this is also A. Suppose I am considering this to be B, and this is also A. So again, because of the presence of plane of symmetry, geometrical isomerism is not possible, and obviously cis trans isomerism is not possible, because for exhibiting cis trans isomerism, the minimum number of B ligands must be 2, right? Now let's check the last option over here, COEN to Cl2. Now En is basically ethylene diamine, so this is ethylene diamine, right? So again, this is a bidentate ligand with same donor sites, so I can represent the complex in this manner, MAA2 B2. B is a monodentate ligand and A is a bidentate ligand. So again, in this complex, how many possible orientations are possible? How many possible orientations are there? Possible isomers are present. So the chelate rings can be trans to each other. As a result, B will also be trans to each other. So this is the trans isomer. And there is one more possibility. Chelate rings are cis to each other, and also the B ligands are also cis to each other. So clearly in the trans isomer, again this will be optically inactive. We are able to see plane of symmetry, horizontal plane of symmetry. Upper end of the molecule will be the mirror image of the lower end. Upper end of the molecule will be the mirror image of the lower end. So again, optical isomerism will not be exhibited over here. But in case of the cis isomer, clearly we are able to see no plane of symmetry or no center of symmetry. So both the elements of symmetry are absent. So it can exhibit optical isomerism. So in option A, geometrical isomers, cis trans isomers are possible, and the cis isomer can also exhibit optical isomerism. So in option A, both two types of isomerisms are possible. So A should be the correct answer. Now the next question is very simple. Obviously we know crystal field splitting energy, that will be directly proportional to the strength of the ligands, right? Now how we can find out the strength of the ligands? The strength of the ligands can be obtained from the spectrochemical series. It can be obtained from the spectrochemical series. Now in the spectrochemical series, Cn minus is present at the extreme end. So Cn minus is a very strong field ligand. After that there will be ammonia. After that there is water molecule, and at the very last oxalate ion is present, right? So this is the order for the strength of the ligands. So stronger the ligand, as per the spectrochemical series, stronger will be the interaction between the metal and the ligand. So if the interaction between the metal and the ligand will be strong, there will be more amount of repulsion between the electron clouds of the ligand and the electron clouds of the metal. So obviously the extent of splitting will also be high, and the value of del O will be greater than P, right? So because of stronger interaction between metal and ligand, the extent of repulsion will also be very much high, and because of that the extent of the splitting of the orbitals inside the metal will also be very much high. So the value of del O will increase because of stronger metal ligand interaction. So that's why in option B, cobalt 3 plus is interacting with the cyanide ligand over here. This interaction is very, very strong, right? So because of that, the extent of the splitting will be the highest in option B. Next question. For the square planar complex MABCD, ABCD all are monodentate, I need to find out the number of possible geometrical isomers. So this is metal. This is one possible isomer. So in this isomer, A and D are trans to each other, B and C are trans to each other. So let's interchange the position of C and D. So I will get the second isomer. So in this case, A and C are trans to each other, B and D are trans to each other. Again, let's interchange the position of B and C. I will get the third isomer. So A, C, this is D and this is B. In the last isomer, A and B are trans to each other and C and D are trans to each other. So AD trans, AC trans, AB trans, BA trans, BC trans, BD trans, CA trans, CB trans, CD trans. Similarly, DC trans, DB trans, DA trans. So these are all the possible combinations, right? So all the possible combinations of these trans are actually possible in these three isomers only. So that's why how many possible geometrical isomers are there? So there are possible 3 geometrical isomers are possible in this case. That's why C is the correct answer. Next question, which are non-transitional elements? Now what are transitional elements? Transitional elements are actually those elements which are having incompletely filled d orbital, which are having incompletely filled d subshell. Transitional elements are basically those elements which are having incompletely filled d subshell in ground state or in any stable oxidation state. Now for zinc, what is the electronic configuration? That is 3d10 4s2. For cadmium, the electronic configuration is 4d10 5s2. For mercury, the electronic configuration is 5d10 6s2. So these are the ground states. Clearly we are able to see in the ground states the d orbitals of all these elements are completely filled. So let's check the stable oxidation state. So zinc plus 2 is the stable oxidation state, cadmium plus 2 is also the stable oxidation state of cadmium, and Hg can also exist in Hg plus 2. Now in also their stable oxidation state, only 2 electrons in the outermost 6s or in the outermost s orbital will be removed, right? So after removing the 2 electrons from the 4s orbital in zinc, the configuration will be 3d10. After removing the 2 electrons in the 5s of cadmium, the resultant configuration will be 4d10, and for Ag this configuration will be 5d10. So neither in ground state nor in their stable oxidation state we are able to see incompletely filled d subshell. So that's why these are actually the non-transitional elements. So option C is the correct answer. Now let's proceed to the next question. So we need to find out the order of the magnetic moment. We know magnetic moment is equals to under root of n into n plus 2, where n basically indicates number of unpaired electrons, right? So more the number of unpaired electrons, more will be the value of magnetic moment. Now for manganese, the electronic configuration is argon 18 3d5 4s2. For chromium, the configuration is 3d5 4s1. And for vanadium, the electronic configuration is 3d3 4s2. So after removing 2 electrons from manganese, the resultant configuration will be 3d5. So in Mn2 plus, this is the orbital picture diagram. There are 5 unpaired electrons which are present. In chromium, obviously after removing 2 electrons, the resultant configuration will be 3d4. So 4 unpaired electrons are present in 3d. And in vanadium 2 plus, the resultant configuration after removing 2 electrons, that will be 3d3. Only 3 unpaired electrons are present. So more the number of unpaired electrons, more will be the magnetic moment. So in this question, manganese 2 plus is having the maximum magnetic moment. After that, chromium 2 plus and vanadium 2 plus is having the least value of magnetic moment among the 3. So that's why option B should be the correct answer. Next question. Atomic numbers of vanadium, chromium, manganese and iron are mentioned, and we have to find out which element will show the highest second ionization enthalpy. Now second ionization enthalpy basically indicates the amount of energy required to remove the second electron. Right? Now in case of vanadium, what is the electronic configuration? 3d3 4s2. So after removing the first electron, the configuration will be 3d3 4s1, and after removing the second electron, the configuration will be reduced to 3d3 only. In chromium, the configuration is 3d5 4s1. After removing the first electron, it will be 3d5 4s0, and after removing the second electron, it will be 3d4. In manganese, what is the electronic configuration? 3d5 4s2. After removing the first electron, it will be 3d5 4s1, and after removing the second electron, it will be 3d5 only. In iron, what is the electronic configuration? 3d6 4s2. After removing the first electron, it will be 3d6 4s1, and after removing the second electron, it will be 3d6 only. So out of all these 4, we are able to see when we are trying to remove the second electron from chromium, the configuration is changing from 3d5 to 3d4. Now 3d5 is actually half field stable electronic configuration as per Hund's rule, right? So the magnitude of exchange energy is very much high. Exchange energy is the stabilizing energy. So the magnitude of negative energy or exchange energy is very much high. Now when we are trying to remove one electron, I am reducing the number of exchange pairs possible. So what will happen? Because of decrease in the value of stabilizing energy, what will happen? The system will become destabilized. So in chromium, the half field stable electronic configuration is getting converted to D4. So that is not favorable. So that's why if in order to remove the second electron for chromium, I need to supply a large amount of energy, because the system is actually going from stable electronic configuration to a comparatively unstable electronic configuration. So that's why this change is not at all favorable. The system will try to restrict this change, and that's why if I want to remove the second electron forcefully, I need to supply the maximum amount of energy. So that's why A is the correct answer. Next question. Purple color of KMnO4. Now KMnO4, I can basically represent the compound in this manner: K plus and MnO4 minus. MnO4 minus is a tetrahedral complex over here, right? Now in MnO4 minus, what is the oxidation state of manganese? That is +7. So manganese, this is the electronic configuration argon 18, 3d5 4s2. Now if I remove all the 7 electrons, what will be the resultant configuration? That will be argon 18 only. So even Mn plus 7, number of d electrons will be 0. So if there are no electrons present in the d orbital, obviously dd transition is not possible. So if there is no dd transition, then how can the substance be colored? So in this case, we have to use the concept of LMCT, ligand to metal charge transfer. Now as for CFT, we have to consider the metal ligand bond in complexes is purely ionic, that is 100% ionic. This is the basic assumption of CFT. So in MnO4 minus complex, I need to consider manganese is present in +7 oxidation state, and it is completely surrounded by 4 O2 minus ion, right? So then only there will be transfer of electrons from ligand to metal. So obviously there will be transfer of electrons from the ligand orbitals to the metal orbitals, and because of this electron transition, that's why we are able to see color of the complex. So the correct answer is actually LMCT, ligand to metal charge transfer spectra, and that's why A is the correct answer. So with the help of DD transition, we cannot explain the color because DD transition is not possible. So obviously we need to consider there will be shift of electron cloud from ligand to metal. So there will be charge of electron density from ligand orbital to metal orbital. Since a transfer of electron is involved, that's why it is showing color. So A is the correct answer. So next question. On treatment of 100 ml 0.1 molar COCl3, this should be cobalt. This should be cobalt. With excess AgNO3, 1.2 into 10 to the power 22 ions are precipitated. Okay. So let's calculate the number of moles of COCl3.6H2O, number of moles of complex that is present in 100 ml 0.1 molar solution. So that will be 0.1 molarity into volume in liter, right? So 0.1 into 0.1. So 0.01 moles. 0.01 moles. Now let's check how many moles of precipitate we are getting over here. So number of moles of precipitate, number of moles of precipitate that we are getting. So that will be equals to given number of moles, given number of particles. This should be 1.2 into 10 to the power 22 ions are precipitated. So mainly they are considering Cl minus, how many Cl minus are getting precipitated. So number of moles of Cl minus must be equals to number of moles of AgCl. So this will be equals to 1.2 into 10 to the power 22 by Avogadro's number. So 6 into 10 to the power 23. So we are getting this value to be 0.2 into 10 to the power minus 1. So 0.02 moles. So clearly we are able to see from 0.01 moles of complex, I am getting 0.02 moles of Cl minus or 0.02 moles of AgCl. So clearly from 1 mole of the complex, I will get 2 moles of Cl minus. So 2 chloride ions must be present for every 1 mole of complex. 2 moles of Cl minus must be present in the ionization sphere, or for 1 molecule of the complex, 2 molecules of Cl minus must be present in the ionization sphere, right? So what is the correct representation of the complex? Correct representation should be option D. So in option D, if I dissociate this complex, what will I get? This complex will split into COH2O whole 5 Cl 2 plus and 2 Cl minus. So we are getting 2 chloride in the ionization sphere, 2 Cl minus are present in the ionization sphere, right? So we are getting 2 Cl minus as the precipitate. So from 1 molecule I will get 2 molecules of Cl minus. From 1 mole of complex I will get 2 moles of Cl minus. From 0.01 moles of this complex I will get 0.02 moles of Cl minus. So that's why D is the correct answer. So this question is based on Wonders theory. Obviously you need to do some sort of calculation, but the question is overall easy. Next, question number 62. So this type of isomer is present. Now in this isomer we are replacing 1 ammonia with 1 bromine. We are replacing 1 ammonia with 1 bromine, right? Now this complex is of the type Ma4B2. In Ma4B2, how many possible isomers are present? How many possible isomers are there? 2 different geometrical isomers are present. One will be cis, another one will be trans. So this is cobalt, ammonia, ammonia. So this is the trans isomer that I am trying over here, bromine, bromine. And what is the oxidation state of cobalt in this complex? Oxidation state of cobalt is +3. So this is a trans isomer. When I am replacing 1 ammonia ligand with 1 bromine ligand, then what will happen? When I am replacing 1 ammonia ligand with 1 Br minus ligand, then what will happen? Obviously the Br minus will replace any one of the ammonia ligand present in the equatorial position. So after that I will get this. Suppose if I consider this ammonia is getting replaced, So after this is the resultant complex, right? This is the resultant complex. So clearly we are able to see the bond angle between these two is 90 degree. Similarly, the bond angle between these two is also 90 degree. But the bond angle between these two bromine which are present in the axial position, that is actually 180 degree. So this is actually meridional isomer, right? So obviously if I replace one ammonia ligand in the equatorial position with one bromine, I will get the meridional isomer. Only one isomer is possible in this case because all the positions are ammonia are equivalent. So if I replace any other ammonia with bromine, then also I will get the same isomer. So this is the trans form. Now if I consider the cis form, then what will happen? So this is the cis form that I am trying over here. So again ammonia in the cis form, bromine will also be cis to each other, NH3. So this is the cis isomer. If I replace one ammonia ligand with one Br minus, then what will happen? So in this case ammonia ligands are present both in the axial positions as well as in the equatorial position, right? Suppose if I replace one ammonia in the axial position, then what is the resultant complex? Resultant complex will be COBr. If I replace one ammonia in the axial position, I am getting this NH3. Now this is the facial isomer. This bond angle is 90 degree. This is also 90 degree, and between these two, that is also 90 degree. This is above the plane and this is on the plane. So obviously the angle should be 90 degree. So this is a facial isomer. So when I am replacing the axial ammonia with Br minus, I am getting facial isomer. Similarly, if I replace one of the equatorial ammonia with Br minus, what will I get? If I replace one of the equatorial ammonia with Br minus, I will get this. So this is NH3 Br, NH3 Br. Again this angle is 90 degree, this angle is also 90 degree, but what is the angle between these two bromine over here? That is 180 degree. So this is the meridional isomer, right? So from this complex, from the cis isomer of this complex, I am getting two different possible isomers. I am getting facial isomer when I am actually replacing the ammonia in the axial position, and I am getting meridional isomer when I am replacing one ammonia ligand in the equatorial position. When I am replacing the ammonia in the axial position, I am getting facial isomer. When I am replacing the ammonia in the equatorial position, I am getting meridional isomer. So two isomers are generally obtained from the cis isomer, right? And from the trans isomer, we are able to see we are getting only one possibility, that is the meridional form. So let us check the statements that are being given in this question. So two isomers are produced if reactant complex is actually a cis isomer. Obviously from cis isomer we are getting both facial as well as meridional. It actually depends which ammonia ligand we are basically interchanging with bromine. So when we are interchanging axial ammonia, we are getting facial isomer, and when we are interchanging with equatorial ammonia, we are getting meridional. So statement 1 is correct. Statement 2 is actually incorrect. For trans isomer, only one isomer is obtained, and that is basically meridional. We are able to see over here. So that's why 1 and 3 are the correct statements, and B is the correct answer. Let's proceed to the next question. Question number 63. Okay, this ligand has been provided over here, and this is actually a strong field ligand. So these are the four complexes. I need to check in all these complexes the metal ions, all the metals are present in +2 oxidation state. Now if these metals are getting oxidized to +3 oxidation state, then there will be decrease in CFAC or increase in CFAC. That I need to check over here, right? Consider the first complex over here, CO PHEN whole 3 2+. Clearly we are able to see this is actually a bidentate ligand, right? This is actually a bidentate ligand, and these are the donor sites. So what is the value of coordination number? Coordination number will be equals to denticity of the ligand. What is the denticity of this ligand? 2 into number of ligands. So in all the complexes 3 ligands are present. So all are actually octahedral complexes, since the coordination number of the metal center of in all these complexes is actually 6. Now let's consider this example, CO PHEN whole 3 2 plus. So in this case cobalt is present in +2 oxidation state. This ligand is basically neutral. Cobalt +2, what is the electronic configuration? That is D7. Obviously because of strong field ligand, crystal field splitting will be high, del O will be greater than P. So this will be the scenario, right? So 1 2 3 4 5 6 7. So what is the value of CFAC? So this will be equals to 6 into minus 0.4 del O plus 1 into plus 0.6 del O. So minus 2.4 del O plus 0.6 del O. I am getting minus 1.8 del O, right? If I oxidize cobalt 2 plus to cobalt 3 plus, then after that what will be the value of CFAC? After removing one electron, what will happen? The electron will be removed from the EG set of orbitals. So this one is T2G, this one is EG. So this electron will be removed out. So after removing these electrons, what will happen? The value of CFAC will be dependent on the electrons present in the T2G set only. So the value of CFAC will be 6 into minus 0.4 del O. So minus 2.4 del O. Clearly we are able to see there is increase in the value of crystal field stabilization energy. There is increase in the magnitude of crystal field stabilization energy. 2.4 is the magnitude and 1 point is the magnitude. So higher the magnitude of the crystal field stabilization energy, more stable will be the complex. So obviously when cobalt is being oxidized to cobalt, when cobalt 2 plus is getting oxidized to cobalt 3 plus, stability of the complex will also increase. Now let's check the other options as well. Next one is zinc. Now zinc PHEN whole 3 2 plus. In zinc, what is the electronic configuration of Zn2 plus over here? That is D10. For D10 we already know the value of CFAC will be 0. If I oxidize Zn2 plus to Zn3 plus, the resultant configuration will be D9. And this will be the representation 1 2 3 4 5 6 7 8 9. So what is the value of CFAC? CFAC is equals to 6 into minus 0.4 del O plus 3 into plus 0.6 del O. So minus 2.4 del O plus 1.8 del O, and I am getting minus 0.6 del O. So clearly we are able to see that the magnitude of CFAC is increasing from 0 to 0.6. So because of increase in the magnitude of the stabilizing energy, the resultant complex will also become very much stable, right? Okay. Now let's check the other options as well. Let's check for iron complex. Now consider the third option over here, that is FePHEN whole 3 2 plus. Now in this complex, what is the electronic configuration of iron? Fe is present in +2 oxidation state, so D6. So for D6 low spin complex, this will be the arrangement of the electrons in the orbital. This is T2G set and this one is EG. So 1 2 3 4 5 6. So again the value of CFAC will be minus 2.4 del O. You have to ignore the pairing energy in each of the cases as mentioned in the question. If I oxidize Fe2 plus to Fe3 plus, what I am getting? Fe3 plus is D5. So in D5 this will be the scenario 1 2 3 4 5, and the value of CFAC will be minus 2.0 del O. Now in this case we are able to see when we are oxidizing the metal from +2 to +3 oxidation state, there is actually decrease in the magnitude of CFAC. So in this case, because of oxidation, the resulting complex will be very much destabilized. But in the all other options that we have checked till now, in cobalt and in zinc wala complex, because of increase in the value of oxidation state, the complex was getting more amount of stability. But in this case, in case of iron, the complex will be less stabilized because of decrease in the magnitude of CFAC. So that's why C should be the correct answer, because we have to find out which complex will lose CFAC value when it is oxidized from +2 to +3. So obviously for iron complex we are able to see the magnitude is getting changed from 2.4 to 2.0. So there is decrease in the magnitude of CFAC, decrease in the stabilization energy. Obviously this complex is losing the crystal field stabilization energy. So C is the correct answer. So let's check for D as well. Nickel is present in +2 oxidation state, D8. So again for D8 this will be the scenario 1, 2, 3, 4, 5, 6, 7, 8. So what will be the value of CFAC? That will be minus 2.4 del O for all these electrons plus 2 into 0.6 del O. So overall I am getting minus 1.2 del O. Now when Ni2 plus is getting converted to Ni3 plus, one more electron will be removed. So the configuration will be D7 only, and this will be the scenario 1, 2, 3, 4, 5, 6, 7. So in this case, what is the value of CFAC? That will be minus 2.4 del O plus 0.6 del O. So the resultant value will be minus 1.8 del O. Even in the last option, we are able to see increase in the magnitude of CFAC when I am changing the oxidation state of nickel from +2 to +3. So in option A, option B and option C, the complex will become much more stabilized because of increase in the magnitude of CFAC because of oxidation. Only in option C, because of increase in the oxidation state from +2 to +3, we are getting decrease in the magnitude of CFAC. So option C, this complex is becoming unstable when I am changing the oxidation state from +2 to +3. Let's proceed to the next question. I hope the explanation is clear. Now, question number 64. So this is actually a brown ring complex. This is actually brown ring complex, right? Ferrous nitroso sulfate. So what is the charge on the cationic part over here? That is actually 2 plus. Charge on the coordination sphere is +2, and obviously SO4 2 minus. So what is the oxidation state of iron in this case? NO is present in +1 oxidation state. Water is a neutral ligand. So X plus 5 into 0 plus 1, the overall value is +2. So the value of X is also +1. So iron is present in +1 oxidation state, right? So for iron in +1, what will be the electronic configuration? We know for iron the electronic configuration is 3d6 4s2. Now in Fe +1, the resultant electronic configuration will be 3d6 4s1. Now this complex is actually an octahedral complex, right? Because 6 monodentate ligands are present. 6 monodentate ligands are present. So this electron will be shifted to 3d wala orbital. The electron in the 4s orbital will be shifted to lower energy 3d orbital, right? So after that, the configuration will be 3d7. So this is the representation 1, 2, 3, 4, 5, 6, 7. Obviously, the resulting complex will be actually a high spin complex. Why? Because though NO is a strong field ligand, but the other water ligands which are present along with NO, they are actually weak field. So there are 5 weak field ligands and only 1 strong field ligand. So obviously weak field ligands are dominating in this case, and that's why the splitting of the splitting of the d orbitals will also be less. The energy gap, the splitting of the d orbitals will be less than pairing energy, and as a result, the resultant complex will be a high spin complex. So 3 unpaired electrons are present over here, right? So option B is the correct option. Option A is not correct because the oxidation state of iron is +1. Hybridization of this complex, obviously it should be outer orbital complex. Since this is a high spin complex, obviously the inner orbitals, inner 3d orbitals are not vacant. So the outer orbitals, the 4s, 4p and 4p orbitals will participate in hybridization, and the resultant hybridization will be sp3d2. So option C is also incorrect. Option A is also incorrect. Last, it is paramagnetic, but the value of magnetic moment is not this. So how we can calculate the magnetic moment? The magnetic moment will be equals to 3 into 3 plus 2. There are 3 unpaired electrons, right? So 3 into 5. So under root of 15. So the value will be closer to 4. Actually the value is 3.87. So the correct value of magnetic moment is 3.87. So option D is also incorrect. That's why we have to find out the incorrect statement over here. So B is the incorrect statement. Next question. Mn plus 3 ion, the electron pairing energy P is about this. Del O values are provided. Which of the following is high spin? We know the complex will be high spin if the extent of splitting is less than pairing energy, and the complex will be low spin if the extent of splitting is greater than pairing energy. This is for low spin complex and this is for high spin complex. Now this is a value of pairing energy 28,000. Clearly we are able to see for MnH2 whole 6 3 plus complex the value of del O is 15800. The value of pairing energy is less than the value of del O. So this is the high spin complex over here. So that's why B is the correct answer. Let's check the other complex as well. In case of MnCN63 minus, this is the value of del O. So 38500. And clearly we are able to see the value of del O is actually greater than that of pairing energy. So that's why this is actually a low spin complex. So high spin complex is MnH2 whole 6. Manganese hexaaqua 3 plus is the high spin complex over here. That's why B is the correct answer. Next question, we have to find out the effective atomic number. Now effective atomic number is actually the summation of number of electrons of the metal, central metal atom or ion, number of electrons present in the central metal atom or ion, plus number of electrons contributed by the ligands. Number of electrons contributed by the ligands. Now let's check CrCO6. Let's calculate the EAN value of CrCO6 minus. For chromium, what is the atomic number? That is 24. So in chromium, how many electrons are present already? 24. Now we know carbonyl is actually neutral ligand, right? Carbonyl is actually a neutral ligand. So obviously this negative charge is actually present on chromium. So chromium minus, in chromium minus how many electrons are present? 25 electrons should be present. So total number of electrons in this complex will be 25 plus 6 into 2. Obviously each of the ligands will contribute 2 electrons because they are participating in coordinate bond formation. So each of the ligands will contribute 2 electrons. So for 6 ligands, total 12 electrons will be there. So 25 plus 12, and the value of EAN for this complex is 37. Let's calculate the value of EAN for the second complex, CrCO6. So in this case, what is the charge on chromium? The charge is 0. So chromium is present in 0 oxidation state. Chromium ka atomic number is 24. So atomic number basically indicates number of protons. Since chromium is present in 0 oxidation state, so that's why chromium is neutral over here. So number of protons must be equal to number of electrons. So total 24 electrons are present in chromium in this complex, and obviously 2 electrons will be contributed by each of the ligands. There are total 6 ligands, so 6 into 2. So we are getting this value 24 plus 12. The value is actually equals to 36. Consider the next complex over here, CrCO6 plus. So in this case, the positive charge will be present on chromium because this is a neutral ligand. So if chromium is having the positive charge, so how many electrons are present in Cr plus? 23 electrons are present. Remaining 12 electrons will be contributed by 6 ligands like this. So what is the value of effective atomic number? That is 35. So clearly we are able to see CrCO6 minus is having more EAN value than CrCO6, which in turn is having more EAN value than CrCO6 plus. So obviously C is the correct answer. So the value of EAN for this complex is 37, for this complex it is 36, and for this complex it is 35. C is the correct answer. Next question. So this is a question which is based on practical organic chemistry. Now sodium bicarbonate solution, this is basically can be considered to be a weak base. Obviously this will react with carboxylic acid resulting in the formation of salt. Obviously weak base will react with acid resulting in the formation of salt and water, right? So acid plus base will result in the formation of salt and water. So acid base reaction will occur. So sodium bicarbonate solution will actually react with carboxylic acid. So sodium bicarbonate solution is basically used for the detection of carboxylic acid, because we will get acid base reaction. Now let's check for option B, neutral ferric chloride. Now neutral ferric chloride, it is basically used for test of phenolic group. So with the help of neutral ferric chloride, we will be able to determine whether phenolic OH group is present or not. So this is the reaction. FeCl3 will react with phenol C6H5OH, and it will result in the formation of FeC6H5O6 3 minus plus 3 HCl plus 3H minus. So this complex is having violet color. So when we are reacting FeCl3 with phenol, we are getting this violet color complex, and with the help of this complex we can easily determine whether phenolic group is present or not. So neutral ferric chloride is basically used for detection of the phenolic OH group. So A is matching with option 2, B is matching with option 3. Now next is sodic ammonium nitrate. Now sodic ammonium nitrate CAN test is basically used for detection of alcoholic group, right? So sodic ammonium nitrate is basically used for detection of alcoholic group. So C must be matching with 4. So I am writing down the reaction as well. So NH4 whole 2 Ce NO3 whole 6. This is the sodic ammonium nitrate. It will react with any alcohol and it will result in the formation of CeNO3 whole 4 ROH whole 3 plus 3, and along with that we will get ammonium nitrate as well. So the color of this complex is actually wine red. So wine red or red color complex we will get. So formation of this complex is actually an indication of alcoholic group, right? So this is the reaction. Now let's check alkaline KMnO4. Okay, so obviously alkaline KMnO4 is basically used for carrying out the Bayer's test, right? Bayer's test. So with the help of alkaline KMnO4 alkene, we can actually determine the unsaturation of any group, right? We can determine. So alkaline KMnO4 is a Bayer's reagent. So with the help of Bayer's reagent, we can basically detect whether there is any presence of unsaturation in a particular organic compound or not. So when I am carrying out the reaction, of any unsaturated compound, suppose for in this example I am considering ethene. When ethene is being reacted with potassium permanganate, then I will get vicinal diol. And as a result, the purple color of KMnO4 will get decolorized. The purple color of KMnO4 will vanish away. So because of decolorization of KMnO4 solution, that's why we are able to say unsaturation is present in the organic compound. So alkaline KMnO4 is basically used for the detection of double bond or unsaturation. So which is the correct option? A is matching with 2, B is matching with 3, C is matching with 4, and D is matching with 1. So that's why D is the correct answer. So for detection of phenolic group, we should use ferric chloride because I will get this violet color complex. For detection of alcoholic group, we should use CAN test. Again, we will get a wine red color precipitate. For detection of unsaturation, we must use Bayer's reagent, and in this test, the purple color of KMnO4 will get decolorized. And for detection of sodium bicarbonate, we should use for detection of carboxylic acid group, we should use sodium bicarbonate. So it will result in the formation of CO2, right? So let's proceed to the next question. When a salt is treated with sodium hydroxide, it gives gas X. Gas X, when passed through reagent via brown colored precipitate, is formed. So basically, this is the reaction. So K2HgI4 plus KOH, this is the Nessler's reagent. Now when Nessler's reagent reacts with ammonia, then I will get this type of precipitate, HgO.Hg NH2I. This is known as iodide of Millian's base. And what is the color of this precipitate? The color of this precipitate is actually brown. So in this question we are getting this precipitate, as it is mentioned over here, we are getting brown colored precipitate, right? So this colored precipitate, brown colored precipitate, will be obtained if Nessler's reagent reacts with ammonia. So obviously Y is the Nessler's reagent over here. Y is actually K2HgI4 and KOH. And what is the gas? Obviously X should be ammonia gas. When ammonia gas reacts with Nessler's reagent, we will get brown precipitate of this complex, right? So Nessler's reagent is basically used for detection of ammonia or ammonium group in any organic compound or salt. Clear? So let's proceed to the next question over here. So that's why in this case C is the correct answer. Let's proceed to the next question. Okay. Appearance of blood red color on treatment of sodium fusion. So we are treating sodium with organic compound containing carbon, nitrogen, sulfur. So it will result in the formation of NaCN. Now this is basically Lazine test, right? This is basically Lazine test. So in Lazine test, first I need to add sodium to the organic compound, then only the covalent bonds will be converted into ionic bonds, and then only I can carry out the test. So carbon, nitrogen, sulfur containing organic compound, it will react with sodium and it will result in the formation of NaSCN. Now FeSO4 is being treated with concentrated H2SO4. Now in presence of concentrated H2SO4, Fe2 plus in FeSO4 it will be converted to Fe3 plus. Now this Fe3 plus will react with SCN minus thiocyanate ion, resulting in the formation of FeSCN3. So this is the blood red color solution that I am getting. So this is the layout, appearance of blood red color. So I am getting blood red color when sodium fusion extract of an organic compound, is basically reacting with FeSO4 in presence of concentrated H2SO4. So this is actually a Lazine test. So we need to add sodium to any organic compound, then only the covalent bonds will be converted into ionic bond. So this is the ionic compound that I am getting. It will split into Na plus and SCN minus. We are getting thiocyanate ion. This thiocyanate ion will react with the Fe3 plus and it will result in the formation of this blood red color complex, right? So it indicates the presence of nitrogen and sulfur elements. So that's why option C is the correct answer. Question number 70. A solution of metal ion, any metal ion, I am considering this, on reaction with Ki, it is giving red precipitate. Reaction of the same metal ion with Ki, with excess of Ki, it will result in the formation of colorless solution. So when treated with Ki, it gives a red precipitate, but when the same metal is being reacted with excess amount of Ki, I am getting the colorless solution, right? Now again the same metal ion, when I am treating this metal ion with cobalt plus 2 thiocyanate, I am getting deep blue crystalline precipitate. So in this case, this is only possible if the metal is Ag2 plus. When Ag2 plus is being reacted with 2 Ki, then I will get AgI2 and 2K plus. This AgI2 is actually red in color and this is the precipitate. Obviously this is a sparingly soluble salt, that's why we are getting precipitate. So AgI2 is having red color. Now again, when we are dissolving this sparingly soluble salt in excess of Ki, I am getting colorless solution. So it is because of formation of this complex K2HgI4. So this is actually a red color complex. The first I am treating the metal ion with Ki, I am getting red precipitate of HgI2. Then this sparingly soluble salt is being dissolved in excess amount of Ki. We are getting colorless solution. Now K2HgI4 is the colorless solution. K2HgI4 is actually the soluble complex, not the colorless solution, is actually a soluble complex. So it will be dissolved in excess amount of Ki, and as a result we will be able to see red coloration of the solution. Now again, when the same metal ion is being treated with cobalt 2 thiocyanate, we are getting deep blue color crystal. So the deep blue color crystal is due to the formation of COHgSCN4. So obviously in this case the metal ion is actually Hg2+. So all these three are the tests for detection of Hg2+ ion in a particular salt. So next question, number of POP bonds in P4O10. So this is the structure of P4O10. First we have to draw 4 phosphorus like this. Then we have to insert 1 oxygen in each of the phosphorus bonds. So we have inserted 1 oxygen in each of the PP bonds over here. Normal in case of P4 there are 6 PP bonds. So in order to form this compound P4O10, what I need to do, I need to insert oxygen in each of the PP bonds. So done. So how many oxygens are present in this compound? That is actually 6. P4O10 mein now we have to place the double bonds as well. So this is the structure of P4O10. So how many POP bonds are present? Clearly we are able to see there are 6 POP bonds. So that's why the correct answer is 6. Next question, the number of SS bonds in polythionic acid. Now this is actually dithionic acid, right? 2 sulfur is present. This is actually dithionic acid. When 3 sulfur are present, then it will give rise to trithionic acid. Similarly, when 4 sulfurs are present, it will give rise to tetrathionic acid. Now in trithionic acid, how many sulfur are present? There are 3 sulfur. And how many SS bonds are present? 2 SS bonds. In dithionic acid, how many sulfurs are present? There are 2 sulfur. And how many SS bond is present? Only 1 SS bond. Right? Now we have to find out the number of SS bonds in polythionic acid. Acha. We don't have to find out the number. It is given the number of SS bonds in polythionic acid is N-X. So consider dithionic acid over here. How many SS bond is present? Only 1. How we are getting this value? We are getting this value from this expression. So number of sulfur is 2, and when we are subtracting 1 from the number of sulfur, I am getting the number of SS bonds. Similarly, in case of trithionic acids, how many sulfur atoms are present? There are 3 sulfur, right? And how many SS bonds are present? There are 2 SS bonds. Now how I am getting this number 2? I will get the number of SS bonds if I subtract 1 from 3. So obviously this is N-X. So number of SS bonds will be equals to N-X. N basically indicates the number of sulfur atoms present in the polythionic acid, and X, the value of X should be 1. So in this case we need to find out the value of X. So the value of X is actually equals to 1. So number of SS bonds must be equals to number of sulfur minus 1. This is how we can find out the number of SS bonds. So the value of X is equals to 1. Question number 73. Now basically we need to find out the amount of nitrogen by Dumas method. Now we know how we can find out the amount of nitrogen using Dumas method. So for finding out the amount of nitrogen in Dumas method, this is the formula. So percentage of nitrogen will be equals to volume of nitrogen that is evolved by 8 into W. W is the mass of the organic compound. So what is the volume of nitrogen that I am getting? 31.2. And what is the mass of the organic compound over here? That is 8 into 0.246 gram. So after doing this calculation, I will get the value to be 15.85. So obviously the percentage of nitrogen is closer to 16. So that's why 16 is the correct answer. Only we have to keep in mind this formula, then only I will be able to do the calculation, right? Okay. Let's proceed to the next question over here. Number of sigma and pi bonds in inorganic benzene. So inorganic benzene is basically B3N3H6. also known as borazine, right? So BBB, boron and nitrogen, they will occupy the alternate positions. 6 hydrogen are connected to all the 6 atoms which are present inside the ring. Now ammonia will try to form pi bond with the help of its lone pairs. Boron is having vacant orbital, ammonia is having excess amount of electron density. So obviously ammonia will try to donate the lone pair of electron cloud to the vacant orbital of boron, and that's why there will be formation of 3 pi bonds. So how many sigma bonds are present? Clearly we are able to see there are 12 sigma bonds. And how many pi bonds are present? There are 3 pi bonds. So we have to find out the total number of sigma and pi bonds. So 12 plus 3, the overall value will be 15. So 15 is the correct answer. Last question. Find the sum of oxidation state of both iron atoms present in Prussian blue complex. So this is Prussian blue complex formula. This is the formula of Prussian blue complex. Fe4 FeCN6 whole 3. So I can split this into cationic and anionic part. So Fe plus 3 plus FeCN6 4 minus 3 FeCN6 4 minus and 4 Fe3 plus. So what is the oxidation state of iron which is present outside the coordination sphere? That is plus 3. And what is the oxidation state of this iron which is present inside the coordination sphere? So let's calculate. So X is the oxidation state. Let us consider X is the oxidation state, plus 6 into minus 1. Minus 1 is the charge on the cyanide ligand. And what is the overall charge on this complex? That is minus 4. So what is the value of X? The value of X is plus 2. So iron is present in plus 2 oxidation state inside the coordination sphere, right? So we need to find out the sum of the oxidation state of both the iron. So this is plus 2 and this is plus 3, and the overall value will be 5. If I add up these two values, I am getting 5. So sum of oxidation state, the value will be 5. So that's the end. So thank you for watching this video solution, and all the best for your next examination. Thank you.